Okay, so we've got one last page to do for the Chapter 1 notes, and this is an application, and it's probably going to look a little familiar. It's another mixing tank problem. This time we're going to come up with an equation that otherwise we would struggle to be able to solve without an analytic means like the integrating factor method. So let's take a look at what we've got. It says we have a very large mixing tank. Initially holds 300 gallons of water in which 50 pounds of salt has been dissolved. So really what we're given here, this 50 pounds of salt, we can say right off the start that that's I'm going to use S for the variable for the amount of salt, and that's my S of 0 amount. So S of 0 is 50 pounds. Another brine solution is pumped into the tank at a rate of 3 gallons per minute, and then the water solution is stirred up and then pumped out at a slightly slower rate of 2 gallons per minute. So we got something strange going on here. So we have kind of an inflow of 3 gallons per minute. This is going in. And we have an outflow at 2 gallons per minute, which you can do a little arithmetic there and find out that that means that every minute the tank is getting 1 extra gallon of liquid in it. So it may start off at 300 gallons, but after a minute it's got 301 gallons. After 2 minutes it's got 302. You get the idea. So continuing on, if the concentration of the solution entering is 2 pounds per gallon. So this is inflow here. This is, I'm going to color code. That's 2 pounds per gallon. And the what does it say? First, there we go. First, determine a differential equation for the amount of salt, S of t in the tank at any time, and then determine how much salt is present after 50 minutes of pumping. So we have this idea of inflows and outflows, and one of the nice moves here with these types of problems is to just kind of draw a general picture of what's going on. And I'm no artist, but I'm just going to kind of draw a general shape of a tank. I'm going to have a little make-believe pump that kind of flows out, and there's all kinds of stuff flowing out of that. And then I've also got an inflow pump, just kind of dropping liquid into this thing. Right? It's just water's dripping down into it. And we know that it's starting off with some kind of particular level of water. It starts off with about, what did we say, about 300 gallons of water. And the initial concentration would be 50 pounds divided by 300 gallons. So we have an idea of how much is in there to begin with. But we're really interested in coming up with a rate of change. We want a differential equation, so we want the rate of change in the amount of salt. Okay, the amount of salt at any given moment. And that's going to be equal to some inflow, or I'll call it inflow of salt, minus some outflow. And again, we have some color coding if we want to do it this way. I'd say the inflow, that's what we were using with green, and the outflow, we were using orange for that, to just kind of keep things straight. And again, a real quick kind of subtle idea that rate of change in S of t is going to have units. If we pay attention to the units, that's going to have units of pounds per minute. And that means each one of these terms has to be in pounds per minute. Because in order for an equation to be true, its units must all match. Each term has to have the same units. So that means that when we rewrite this, or when we try to write this as ds dt, and we write our inflow and we say, oh, inflow, that had 3 gallons per minute. That's not good enough because gallons per minute is not pounds per minute, but we know it's flowing in at 2 pounds per gallon, so if we multiply those together, we wind up with the units that we want. We cancel out those gallons, and we wind up with pounds per minute. That's good. That's what we want. The units work. The units tell you what to do. And similarly, we're going to write our outflow, which is going to be the only thing that we really know to begin with is the outflow is 2 gallons per minute. And now we're kind of stuck. We have to come up with something that has basically pounds per gallon, but we're not given that up here. And so what we're going to do is we're going to write this thing. We're going to create our little factor here that basically says what's flowing out of the tank has a particular concentration, pounds per gallon. And so the pounds of salt that are in here at any given moment are just S of t. And that's pounds. I'm just going to write the units next to it. But the number of gallons that are in the tank at any given time, we already said, depends on how much time has gone by. At 0 seconds, there's 300 gallons of water. But at 1 second, or I should say 1 minute, there's 301. At 2 minutes, there's 302. So basically what we have is 300 gallons plus however much time has gone by. So it's 300 plus T. And that's gallons. And if we did this right, then the units, gallons up here, gallons down there, are going to cancel and we're left with pounds per minute. All of them have pounds per minute. And so I'm just going to make a little note that this down here, this 300 plus T, that's the amount of tank, or amount of water that's in the tank. It's 300 plus T. And the plus T comes from the fact that we are in minus our out equals 1 gallon per minute. That flow. And so that coefficient that's sitting in front of the T is a 1 because it's 1 gallon per minute. That's where it's coming from. Oops, let me scoot that up. So if you were to face a different problem, for example, if it were instead of 3 gallons per minute and 2 gallons per minute, if this were 5 gallons per minute and 1 gallon per minute, the difference, of course, there would be 4. So instead of going up by 1 gallon every minute, it goes up by 4 gallons every minute. You get the idea. So this tracks, this works in different contexts as well. So now that we're convinced that the units work out, let's go ahead and simplify our equation, get rid of all these units, and just focus on what we have left, which is 6. There's no factor, no variable involved here. It's just 6 minus 2 times S divided by 300 plus T. Scoot that up. And at this point, we have a linear, homogeneous differential equation that we can use our integrating factor with. You'll notice there's our variable s. This has an s term over here that we can kind of slide to the other side and begin the process of the integrating factor method. Now, I'm not going to list all the steps, but you get the idea. So I'm going to scoot this down so that we can actually write out what's going on with our integrating factor procedure here. So let me get a slightly different color so we can write this, then keep track of it. So we have ds dt plus 2 over 30, or excuse me, 300 plus t. I don't know why I wrote 30 there. It should be 300. If you were paying attention and caught it, good for you. And this is times s. The other side of the equation is just plain old 6. And so what we need to do at this point is figure out what our integrating factor method is, or what our integrating factor is. And so remember, we're looking for mu of t, and that's going to be this guy right here. That's going to go up into the power e to the integral of 2 over 300 plus t. dt. And so we're going to integrate that with a little bit of effort. It's not that bad. This becomes e to the 2 natural log absolute value of 300 plus t. Ignore the constant. And when you pull the 2 inside, make it a square, the e and the natural log cancel, and you wind up with the integrating factor is equal to 300 plus t quantity squared. So that's what we're going to multiply through this equation right here. It seems like it would be super ugly and nasty, but notice this thing squared, it's going to wind up canceling with this guy right here, and it's going to become a little bit more manageable. So I'm not going to color code everything, but I am going to kind of write it out here. So we have 300 plus t quantity squared times my entire differential equation, ds dt, plus 2 over 300 plus t times s equals 6. And so I'm going to kind of move us along here and say, multiplying it through, we're going to wind up with getting the result is going to be d dt of quantity 300 plus t times s, squared, times s. It's going to be that thing. That's going to be the derivative of this. That's what's left as a result of the integrating factor method. The other side is just 6 times that same integrating factor, 300 plus t quantity squared. So if we do it right, then the result of our integrating factor method is just our integrating factor times our dependent variable. That's what's left. And so if we integrate both sides with respect to t, on the left, we're integrating the derivative, so it just kind of falls away by itself, and we're left off with 300 plus t quantity squared times s equals, this side we're integrating with respect to t, which is not a terribly difficult integral. It's just kind of a power rule, a little quick u substitution. You'll convince yourself that this becomes, the new power is 300 plus t to the power 3, and because that becomes 3, the thing out front is going to be 2, and we have plus a constant. Do a quick division to wind up with our function for s of t, our general solution for this. When I divide it out, it becomes 2 times 300 plus t plus constant times 300 plus t to the minus 2 power. Or you can write it as a denominator if you would like. So this is our general solution. So now what we need to do is use our initial condition. If you remember way at the top, the initial condition s of 0 equals 50. And so if s of 0 equals 50, that must be equal to all this when t equals 0. So this is just 2 times 300, or 600, plus a constant times 300 plus 0 to the minus 2. That's just 300 to the minus 2 power. A little bit of arithmetic, and we subtract the 600 from both sides. We get negative 550 divided by this thing, which is already a negative power. So we have negative 550, constant is equal to negative 550 times 300 squared. And that's the exact value. I don't have a calculator handy on me, but that's the exact value of the constant. That means that we know my particular solution, which I'm going to use green to kind of indicate the particular solution. I won't use green. Let me use something else. I'll use purple again here. This right here is my particular solution with the initial condition. It would be 2 times 300 plus t plus this constant right here, which is negative 550 times 300 squared, times this guy right here, which is 300 plus t to the minus 2 power. Blech. And what we're interested in is getting an approximate value for what happens when t is equal to, I think if I remember correctly, after 50 minutes of pumping. So this is going to be what we're interested in predicting. So we want to predict that. So way down at the bottom, now that we've got our particular solution, we can actually figure out what S of 50 is approximately equal to. So if you give me a second, I'm going to hop on a calculator and see if I can figure it out. So without getting my undies in a twist, I just grabbed my calculator and put this in there, and I wound up with something like 295.9. And because this is an amount, this is the amount of salt, this is pounds, and that's what we can expect, 295.9 pounds. Now, keep in mind that prior to knowing the integrating factor method, we would have gotten to this part right here and either used a lucky guess method, which would not have been pretty, or just hopped on maple because that was the only other way to do this. So the integrating factor method gives us another algorithmic strategy for being able to solve these differential equations that are linear in nature, and it always works. Doesn't mean it's always pretty, but it definitely always works. So I'm going to leave us off there, and remember I'll be posting not only the completed version of the notes, but I'll also be posting a maple file for you to be able to monkey around with and check out, in which I do some of the kind of work for these problems and verification of these problems. So have a good time, fill out the notes, and I'll see you on Thursday ready to go to take part one of the exam.